Well, hello everyone, and welcome to Multiple Linear Regression Prep. So here we have a data set. This is stadium data. And with the stadium data, we're looking at gate receipts. In other words, how much money comes in the door from selling tickets. And then these are for different events that took place. So think of these as, either different days, different weeks, different dates effectively. And then leading up to those gate receipts are the amount of money that was spent in television, radio, newspaper, magazine, mailings, mail postal, internet, and sales promotions. And what management would like to know, based upon all this data, is which of these television, radio, newspaper, magazine, mail postal, internet, and sales promotion is most effective at driving traffic to the gate. I mean, obviously all of them in all likelihood have some effect, but the question is which ones have a significant effect, effectively a provable significant effect in driving traffic. Because those are the ones that we would like to double down and spend even more money on to drive even more traffic, and then obviously not spend too much money on the ones that aren't effective. So this is a bit of a detective game, and this is where multiple regression really excels, because we can dump all of these numbers, this whole table, into multiple regression, and it can tell us one at a time which one is least effective, right? In other words, not significant. And we can drop that one out of the model and then run the model again and see, okay, now which one is least effective, drop that one out, and keep dropping them out until all we're left with are predictors that are significant. So let's watch how it happens. So I'm going to go over here to the MLR tab. And what I'm starting with on the left is this is the same data. Just dropped off the dollar signs. But the way that I got this data is with a great function in Excel called choose columns. And if I put choose columns and then I highlight the data set, which is on the stadium data tab in those cells, and then after that I put a comma and I list, comma separated, the columns 1 through 8, because there were 8 columns, then it will bring back all 8 columns. And up here, just to remind you what those columns are, column 1 is gate receipts, 2 is television, 3 is radio, 4 newspaper, 5 magazine, 6 mail postal, 7 internet, and 8 sales promotions. And this will become very important because as we eliminate columns, we will want them to drop off the list. And we'll be able to do that simply by erasing the column number from this formula, and then the formula will remake. I'm going to show you how that would work. So for example, let's say I happen to know that newspaper is going to be the first one to go. A little preview. So let's say I took out newspaper and its comma. And you see how I got the data set now with that column missing. I'm going to undo that because we need all the columns for the first one. Okay. So we're doing backwards multiple regression, looking for which coefficients are significant. So let's go ahead and run our data analysis toolpack. So we go to data and go to data analysis and pick regression. And our Y range, what's being predicted, are the gate receipts. So we highlight gate receipts and then all the way down that whole column. And our X range are going to be all the other columns. So starting with, it's having a hard time highlighting for me, TV, all the way down. And we do have labels. And our output range is going to be over here, where it says summary output. Click OK. And now we've got our output. So when we look at this output, the first thing you do whenever you're running regression, well actually first thing I always do, just so the numbers kind of make sense, is I will highlight And especially for the first one. If you don't do it for all of them, maybe not the end of the world, but at least for the first one, try to get a feel for the numbers by highlighting them and reducing it to 2 decimal places. And even on this one that's really wide, I can do that. Okay, so let's look at this output. So, in particular, what we're really after when you first run multiple regression is this section here that says ANOVA, which stands for Analysis of Variance. And all of these numbers are going into calculating this very last number that is in the ANOVA, the number called significance F. And that tells you whether or not any of these predictors that are listed here is actually having a significant effect. And how do we know if it is? We look to see if that number is less than alpha. Alpha is 0.05, so that number is certainly less than alpha. So that means we can keep looking, that yes, something is going on. So that's exciting. So that's step 1 here. First, look for significance F in the ANOVA output. If less than alpha, then at least one predictor is significant. All right, then we remove the coefficients in the model one at a time, starting with the highest p-value, the least extreme t, and repeat until only significant coefficients remain. So let's see what that looks like. So first we'll start up here with the distribution. It's a t distribution. The case is two-tailed, and that's just what's always going to be true in regression. It's always going to be t two-tailed. The alpha will change, but the problem with this one is 5%. All right, now we need the degrees of freedom because this t-distribution changes shape depending on the degrees of freedom. And that is, you've got 3 different numbers that are candidates for degrees of freedom. The number that we use is the one that says residual. And just to give you a feel for where these numbers come from, we start off with 30 observations, right? It's you always have at least -1 degrees of freedom, so that's where the 29 comes from. And then we have 7 predictors in the model, so we have to subtract that off 2. And so that's how we end up with the 22. So effectively it's 30 -1 -7, and that gives us the 22. So this number we'll use each time, the residual, but that number will change because as we reduce the number of predictors, the residual will go up each time. So now it's 22, for the next one it'll be 23, and so forth. All right. And then as far as our variables go, the first variable is the intercept. And then we'll copy this down. And our t-stat is here, so it's not right next door, so be careful. We ignore the next 2 columns, so go all the way to t-stat. Copy that down. And then this one we can actually copy across since p-value is right next to t-stat. See it there. All right, now we look at the diagram. And what we're after is eliminating the predictor with the highest p-value, right? In other words, that's the one that could easily have occurred by chance because it has a really high p-value. And literally the highest p-value will be the highest dot on the curve because the height of the curve is the probability. So there it is, it's newspaper. It has a p-value of 0.47. And curiously enough, it also has the lowest t value, lowest meaning the least extreme, I should say, meaning closest to 0, all of which makes sense, right? Because as you come in close to 0, you go higher up on the curve. So you can actually clearly see the relationship between t and p and why as t gets less extreme, p gets higher on the curve, which is why you have a higher p value. So anyway, so newspaper goes. And then we come over here and we have to take it off this data because we're going to run the data analysis toolpack, but we want to run it without this column here. And the easiest way to get rid of that column is to edit this formula and take out the 4 and the comma that goes with it. Okay, and then we run the data analysis toolpack once more. So back to data analysis. They should go a little bit faster because the Y range will still be the same, so we don't even have to mess with it, right? Because it's the first column, it will always be the first column. And then the X range, though, does change because it's going to be 1 column less. So we highlight again, but one column less. And the output range will also change. And we'll drop it here in the second summary output location and run it. All right, and now as promised, the residuals went up by 1 because we only have 6 predictors, so we're only subtracting 30 minus 1 minus 6 this time, and that's what gives us 23. And the variable is the intercept. And the t-stat. And the p-value. Oh, I could have just copied that because they are right next to each other. All right, now who's highest? The internet is the highest dot now. And also notice how the internet dropped. It had been way up here. After newspaper dropped out, internet dropped down here. Why? Why didn't it stay up there? And the reason is because all of these variables interact with each other. There's something called multicollinearity, where they actually do influence one another. So when you take one out, it actually does affect everybody that's left. Usually they keep somewhat relative positions, but they do move around every time somebody comes off. So we're going to eliminate internet. And then we have to eliminate it here as well. So internet is number 7 in the formula. So we take out 7 and its comma. All right, and then we run the data analysis toolpack again. Remember, the y doesn't change, but the x's will, because now we have to reduce it again by 1 column. And the output range goes to the next summary output. Okay, the residuals went up by 1 because we only have 5 predictors now. So it's 30 minus 1 minus 5. And that gives us 24. There's the variable, and there is the t-stat, and the p-values. All right, so who gets eliminated now? And as you can see, the highest dot on the curve is radio. So radio is the next one to go. Now, could I have gotten it from here, or actually even from here? Yes, I could have, as long as I'm very careful, because over here, radio is the highest number, but notice how the intercept number is creeping up here, and it is possible, in fact, I think it might happen on the next run, that the intercept value will be even higher than any of these numbers, and that's a problem. So you never eliminate the intercept. In fact, on this drop-down, we don't even offer it as an option because you can't eliminate the intercept, right? You can only eliminate a predictor variable. Even though it sort of seems to be part of this list, it's kind of its own thing. Okay, so radio's dropping out. So back to our formula, and radio is number 3, according to this. So 3 drops out, and its comma. And then we run it again. And you can see we have to reduce the x values one more time. The y stays the same. And the output range changes as well. Okay, so the degrees of freedom at 25 now, which makes sense. 30 minus 1 is 29, minus 4 is 25. And the t-stats are here. And the p-values are here. Right? So you can actually see this is exactly what I was afraid of. The intercept has the highest value, but we can't eliminate the intercept. So we got to get the next one that's not the intercept or the highest value, which is mail postal. And you should be able to see it over here. In fact, you can see it is just outside of the green area, right? And P 0.08. 0.08 is higher than 0.05. That's why it's not significant. So mail postal drops out. And we need to drop it out of here too. Mail postal is number 6. So back to the formula and kill 6. By the way, if you ever mess up on this, just put all the numbers back and then, with the commas, and then figure out, which one. This is non-destructive because the data actually isn't here. The data is here in Stadium data, and we're just effectively extracting from it in real time. Okay, let's look at regression. The X range is going to change. Now we're down to 3 columns. Hopefully this will be the last one. And the output range is here. All right, so the degrees of freedom, 30 minus 1 is 29, minus 3 is 26. So, whoops, click here for the degrees of freedom. And then our variables, there's the intercept and the t-stat. And the p-value. All right. So as you look here, you can see that all of the predictors are in the green, meaning their p-values are less than 0.05. The only one that's higher is the intercept, but as we said before, that's not even plotted, and that one doesn't go. Okay. So now we're ready for our regression equation. So gate receipts will be equal to, right? The regression equation is who's left as a significant predictor. So it's going to be some number times TV. That's television is the first predictor. Well, what's the number? The number that you use is the coefficient. So what I'm going to do to make this clear is do the formatting of the numbers again so we can really see what these numbers truly look like. Like I said, I usually like to do the first one and then the last one, just to make sure I get a feel for the numbers. Because of all those decimal points, it's hard to. Okay, so as we look here, it's these coefficients. So gate receipts is going to be equal to 3.57 times TV, plus, and then we need the coefficient for magazines. So equals the coefficient for magazines, plus the coefficient for sales promotions, plus what comes at the end? Our intercept. So there's our intercept right there. Oops. I guess I gotta put an equal sign here to get it. And there's our regression formula. Now, when we are doing a prediction interval, which is what this is down here, the 95% prediction interval, first we want to actually calculate the gate receipts. And this is where the prediction comes in handy, because these are new numbers. In fact, they're higher numbers than we had in the original data. So we're trying to predict, based upon these new higher numbers, what would happen to gate receipts. Let me just prove that to you. So you'll see that none of the numbers here, or very few of the numbers here, were over 100,000 for the predictor variables, and yet down there I picked all numbers bigger than 100,000. And our gate receipts never got over 1 million. But if we've done this right, then even though we're going to end up spending a lot less money overall, even though we're going to jack these 3 up the overall spend is going to be down. Our gate receipts should go up because these should be the most significant or basically biggest bang for our buck predictors. So let's see if that happens. So our formula is equal to 3.57, oops, and which I need to log because it's not here, not in this table, times the TV value that we're going to try, plus the 2.24 locked times the magazine value, plus 4.32 locked times the sales promotion value, plus the intercept, which gets locked also. And look at that. All of a sudden, even though we've spent a lot less money overall, all told, we're going to actually end up bringing in more money on the gate receipts. So this is really good for business. By basically honing down and figuring out what made a difference, we can spend less money and make more money spending less money, which is what business is all about. Okay. So now for the prediction interval, we have to subtract. So it's going to be equal to this number minus 2 times the standard error. And that's the standard error for the whole model, which is this one here, which gets locked. And that gives us the lower bound of the prediction interval, which isn't, which is still, it's actually surprising that we can get that close, considering it's not a huge sample. And then you have to ask yourself, well, how can we get that close if it's not a huge sample? And the reason is really interesting. It's this number right here, the R squared. In other words, this model is predicting 99% of what's going on. 99%, that is really high, right? So we've got a model that's almost perfectly, even based on this small data set, we've got a model that's so closely predicting what's going to go on in the population that we can actually have a pretty tight prediction interval even for the population. So that's kind of cool. In other words, we can be pretty confident about these predictions. All right, let's look. And by the way, that rarely happens in the real world, but one can dream. Okay, so then to get our gate receipts at the high end, it's going to be equal to that plus 2 times this same standard error, and lock that, and then drag down, and we get our full points for the problem. And you have just done the magic of multiple regression. One thing that's really fun when you're all done is to come back here and actually just sort of, flip through and see what happened, right? We started out with all these predictors, then we dropped off newspaper, we got down here, then we dropped off internet, got down here, dropped off radio, got down here, dropped off mail postal, and then we were left with these 3 predictors as being the significant predictors, the biggest bang for the buck. And we can actually see just what the bang is. We can't isolate them though, because there could be, we can't say, oh, well, sales promotions has the highest number, 4.32, so we'll only spend money on sales promotions, because there is interactive effects. It's like a recipe. You need all 3 at the same time to get all the interactive effects that are predicted by the model. And that's all we have for this time. I hope you've enjoyed the multiple regression. It really is one of the most incredible things that we do in statistics and analytics.